Okay, let's start from scratch. So today's demonstration is about Unicity EVM, which is a Ethereum-compatible blockchain under Unicity PFT core layer. And we have specific goals why we need an EVM instance within our infrastructure. Because EVM and Ethereum world is basically de facto standard of decentralized finance. And we can achieve lots of business functionality by just copying, pasting template smart contracts, like OpenZeppelin has a good library for implementing interesting things. And one important functionality is interfacing with external exchanges. Exchanges expect EVM interfaces or RPC APIs offered by an EVM blockchain. And Ethereum has a great standard token library. ERC20 is what we know as a token, as a fungible token. Then there is a non-fungible token, and so on. We are all well standardized. So we can take our Unicity assets, import them into the EVM, and everybody can transact with them with like very familiar interfaces. And another use case is that if you need to have a functionality with lots of involved assets or tokens, or a pooled asset, like implementing a liquidity pool-based exchange or implementing a lottery. Now, lottery means that we take like a couple of parties. We are putting their tokens in a big pool, and then based on some event, one of the parties gets all the tokens back. So if you implement it based on Unicity tokens and predicates alone, then it's complicated without a trusted third party. And then just plain simplicity, parallel composability is like very easy to do compared to sequential composability. Because within one EVM round, all the contracts which depend on each other either execute or none of them execute. It's basically atomicity for free. And then we can use EVM to implement all kinds of programmable rules for the Unicity platform, to do governance based on Unicity token, to implement tokenomics, to incentivize certain things within a Unicity network, and so on, because the functionality offered by the proof of work chain at the top of the consensus layer is rather limited. And of course, we need transparency for certain kind of tokens. It's for compliance reasons. And because the demonstration talk takes a moment, I'll show how it looks like. All the setup is in my own machine. It has a copy of BFT core and one node Unicity EVM machine, which includes a sequencer and prover. And it takes a moment. Okay. I start a root chain just to be sure I cleaned up everything. And I start the EVM process. So it starts with Genesis. It certifies the Genesis record. Genesis is kind of simple. But anyways, let's scroll back, see what's going on. First, it obtained the Unicity certificate for synchronization. It does not certify any blocks. And what happens is that we are certifying the Genesis record. And it happens immediately without proving, because there is nothing to prove. with Genesis record, we can just have to trust it. But basically, we see that the node is started up. It's connected the BFT core using BFT core specific APIs, libp2p and CBOR serialization. And let's make some transactions using the test, alloy, and so on Ethereum tools chain. Okay, I'll increment the nonce manually. And now there are 5 transactions. So what happens here, we see that, okay, it's already started proving things, but basically it creates a block, created already a block with 5 transactions. This is gas amount needed. And now this is already the start of ZK proving using the SP1 prover. Some statistics, and now it takes something like 5 minutes to go on. We just mark the line and return here after looking some more slides. Okay, so this is the goal why we are doing it. Okay, now you can see it. So the choices, the EVM basically has to be implemented in Rust because Rust is the only language which has necessary zero-knowledge tooling. Well, of course, other great EVM implementations in other languages like Go and C and so on. So we are using specifically ZK VM and not ZK EVM. The difference is that ZK VM takes a full implementation of EVM block verifier and runs it in a virtual machine and then generates execution trace on it and proves it. But ZK EVM is specific to the virtual machine implementation, so that all the instructions of EVM have to be manually written as zero-knowledge circuits. It's more complicated, and it's much harder to extend with custom precompiles. They all have to be implemented as a custom circuits in case of ZK EVM. But in case of ZK VM, the precompile security comes basically for free. So risk 5 is a VM instruction set because it's like a de facto standard of anything which works in production. Others being WebAssembly, which is a higher level but less efficient. It has like funny memory model, which is not efficient on ZK. Then Lisp, and there is a Starkware stack based on Cairo language, which are more specific, all of them. But RISC-V is like the most general VM. And there are basically 2 production-ready ZK VM implementations, SP1 and RISC-0. And I just chose SP1 because I like it more. I think it's mostly because it's a second mover. RISC-0 was first one. It took some decisions, but SP1 learned based on the choices and did some stuff in better or more general way. So there is, I think, that more freedom to do stuff on SP1 platform than RISC-0. And then finally, we need a good implementation of EVM in Rust. So the obvious choice initially seemed to be REVM, but when I found that there is a kind of recent implementation of full Ethereum layer 1, layer 2 called Etrex, which implemented by the Lambda class. And the main reason is that it has less lines of code than all the other implementations. So this is a Etrex implementation, and this is RETH, which is based on REVM, basically. 4 times less lines of code. And I think that there are less abstractions because of the beauty of doing abstract things as well. So it's more down-to-earth implementation. And we are using it as a base platform to implement our own layer 2. So we are not using its layer 1 functionality. And it has a great interface to plug in different kind of block validity proving backends. I think there are even 3 ZK EVMs and certain trusted execution environment, which is Intel TDX. TDX is not a hardware level execution environment, it's just VM, which is attested using the hardware counters. But certainly it's better than nothing. But everything still together is kind of complicated, still like order of magnitude more lines of code than, for example, our aggregator written in Go. And of course, it depends on what kind of libraries we are using, but Rust ecosystem has like really great cryptography libraries available. And now how it integrates with our own layer 1, which is part of Unicity consensus layer. We call it BFT core. Here is a picture. The proof of work and BFT core together are the aggregation layer, and the Unicity Oracle runs under the BFT core. So basically what the BFT core does, it's like very close to what layer 1s are doing. It accepts summary certification requests, validation requests, and returns a certificate to whatever is running at the layer 2. And in case of uniqueness Oracle, the validation is kind of simple. It's just necessary to validate if uniqueness Oracle is not forking itself, and if it doesn't delete anything within its aggregation tree, and that's all. But in case of Unicity EVM, it's necessary to also prove that the EVM has consistent state transfers without forking itself, and all the state transfers are valid. And there are many ways how to prove the correctness, and we will show it, how it works. So, but the main limitation of BFT core is that, no, I wouldn't call it a limitation, but it's a different setup. Means that it doesn't have its own blockchain. It has only cumulative state. It doesn't have blockchain. It has state, which results in executing all the previous blocks, if you can call it. The blocks are virtual, in fact. And it means that it cannot provide data availability. So there is nowhere to submit the blobs. So we had to implement data availability in some different ways. But it returns Unicity certificates, which can be validated immediately, right away, just based on the Unicity trust base, which is kind of compact root of trust. So the main benefit is that instead of running own instance of validator, it's just possible to download the Unicity trust base and use it as a root of trust and still validate everything. And then eventually the state of a BFT core is also committed to the proof of work layer, so for a maximalist level validation. And integrating EVM machine with Unicity infrastructure has, in fact, 2 kind of independent layers. One is an infrastructure level integration, so that our BFT core certifies whatever the EVM is doing, and another one is the token layer or token level integration. And it means that our layer 3 or our token layer tokens must be verifiable for contracts running in EVM and vice versa. So the token layer users must be able to efficiently validate everything what happens in EVM, to validate events, to validate transactions if they are executed or not. And it's done correctly if the both of the parties do not have to basically run a full validator of another layer to be able to communicate with each other. And so how it can work. In order to be able to validate token layer tokens, we provide a system level built-in or system contract which has access to the root of trust, Unicity trust base directly, and it can validate let's say the anchor on top of aggregation tree on top of transactions in Unicity token or records in Unicity tokens, without nobody having to implement full, let's say, validation of Unicity tokens based on plain Solidity code, which otherwise would be necessary if you, for example, are validating Unicity tokens on main Ethereum instance, for example. And the other way works just by inserting Unicity certificates into EVM blocks so that they certify block headers so that anybody can just extract a compact proof of the transaction being executed or the contract firing an event. We just extract Unicity certificate, extract hash tree until the specific artifact, and send to anybody, and with anybody, if it is in Unicity network, and validate it right away.
Cool.
So main difference compared to normal Ethereum layer 2s is how the execution loop is implemented. Because like in layer 2, ZK rollups, they are basically cheating. They have a centralized execution because they have like a single sequencer and single ZK prover, and they return to users immediately that they have already accepted the transaction, and user receives soft finality signal as a receipt. And this is not, in fact, equal to the strong finality, which can be achieved only after committing to actual layer 1 blockchain. But if layer 2s are big enough, then these finality failures are very unlikely. Nobody wants to allow it because it provides horrible experience, but still it's centralized execution by the party who runs layer 2 sequencer, prover, and the stack, rest of the stack. And what else on layer 2 is done that every individual block is not proven in ZK. In fact, usually the blocks are patched. So, for example, they collect blocks for 1 hour and then generate final proof because proving costs and layer 1 committing costs to amortize. So there are less main layer 1 block fees or transaction fees if many transactions are bundled together with one amortized proof, and also proving effort is lighter if it's done in a batched way. But we do the execution loop differently. And the main reason why we do it is that layer 1, the BFT core, is fully under our control, and we don't have to do anything possible to optimize the size of a proof. So instead of like 200 bits proof, which still costs like $10 to validate on Ethereum, we can have like megabyte size proofs if necessary, and BFT core validators do not complain as long as we are not running like hundreds of EVM instances under our BFT core. So how it works? First, we collect transactions. We put together a block. We execute the block up, and then prove or create a zero-knowledge proof that the block was executed correctly. And then we submit proof together with state transfer requests to BFT core as a usual transaction, usual with BFT core Unicity certificate request is the name of the transaction. And then pretty soon we receive back a UC, Unicity certificate, and can finalize a block. And right now I have implemented it so that it's a one big loop, but instead we can run sequencing and executing next block parallel during the proving time already. So it's a bit optimistic, but we can roll back any time. And let's jump back, see how we are doing in another window. Okay, when we jumped away, we were at this position. And we see that less than 4 minutes and something later, we actually generated SP1 proof. We have 256 public value bytes, and the proof size is 1.5 megabytes. And now we are creating a certificate request, sending it to the layer 1, submitted it, and in 3 or 4 seconds, we are receiving back the Unicity certificate, which is validated, accepted because it passes all the checks, and now it's declared to be finalized. And now we are waiting for next transactions to create new blocks and so on. Okay, but this is basically the demo part. Just let's continue discussing about what kind of proofs there can be, and because we have this extra freedom, we don't have to use this very small 200 byte proofs. What Ethereum layer 2s are using, we can do anything. So, for example, we can have no proof at all. Instead, we just commit the state transfers, and the only thing what EVM layer is forced to do is that it's like subject of this uniqueness proving of BFT core. So what happens is that the EVM machine cannot fork and cannot backdate previous blocks. So this is just the basic uniqueness proving functionality, which works even without modifying the BFT core protocols. And it scales awesomely, of course, because there are no proofs. So second option is that EVM is a cluster of machines, and we implement honest majority-based voting about the blocks. It's rather easy to do, but the trust requirement is that we have an honest majority of EVM validators, and we have honest majority of BFT validators, which are eventually validated by proof of work and end users. But still having 2 layers of honest majority is kind of ugly. So it's not like really awesome, but it scales well. So third option is ZK. ZK has like different assumptions. We assume that cryptography works, and Starks, as far as I know, do not have formal end-to-end proofs of being correct. There are still gaps in their analysis. And if you want to have a small ZK proofs, then there is also dependence of a trusted setup, which is considered pretty ugly, but it's manageable using multi-party computation. So scaling means that proving is very slow, verification is constant time, and we can have as many ZK EVM shards as we want. So it scales well at the validation side, but it scales hardly at the proving side or client side. So there is another option. We are providing entire block in a package so that it can be validated by a light client to BFT core nodes. So basically it means that instead of sending compressed ZK proofs to BFT core validators, we take entire block, or we take the input which goes into ZK prover, and instead of proving it locally, we send the input straight away to BFT core machines. So instead of verifying proofs, we actually verify the input to proving. And by doing it, they verify if block and state transfer are correct. So this kind of option is not possible for other layer 1, layer 2 ZK VMs, but because of we run our BFT core ourselves, we can afford it. And I tried to paint the scaling comparison right here. The bright red one is this light client mode, and we see that the layer 1 validation effort grows linearly if you add more transactions to the block. And eventually there is this hard verification scaling limit, which is at the layer 1 side. So basically no effort to layer 2, but layer 1 has to validate all the transactions, which eventually presents a hard limit where we cannot scale anymore. And the darker red is Starks. The proof is a bit bigger, as I said, 1.6 megabytes. We see that, but it takes less effort to prove. So this vertical line here is just proving effort limit. We just cannot afford to add more hardware, so there is a hard limit how many transactions we can put into a block. But layer 1 doesn't care. The limitation is at layer 2 side. So if you have a small proofs using Prof 16, then the proving effort limit comes faster. And there is a final option is to use this trusted execution environment or N of M consensus. This is this cluster of machines or TEE, which are even more efficient and they scale more until there is some kind of like execution limit that no, I think it's not execution limit, it's more like a bandwidth limit what the BFT core can afford. So yeah, the final option is trusted execution environment. It means that we have a remotely attestable virtual machine which validates a block, and CK and our EVM, our BFT core machines just trust this attested machine. In theory, it scales awesomely, but in practice, there is like lots of administrative processes, and I even do not know, maybe we have to trust system administrators, which would be super ugly. And we have to trust hardware, we have to trust Intel of managing their keys and whatnot. And a bit more details. There are like 3 different kinds of ZK proofs. This is 1.5 megabyte, which I demonstrated. which is a recursive Stark. Proving is hard, verification is simple. When there is an input, so-called core proof, which grows linearly, a bit less hard to generate. Maybe we save a minute from proving time if we use the core Starks. When the next step is having a graph 16 ZK proof on top of compressed recursive Stark, which all the other layer 2, layer 1s are using. It's even harder than the first one here, and depends on trusted setup. If you have the trusted execution environment, proving is simple. Verifier has to pray and hope the best. I don't know. It depends on organizational stuff too much for decentralized things, I believe. So it's hard sell. If we are running this light client mode, the proof size is basically all the transactions, and whatever is needed for a light client to verify, it's basically a list of touched accounts and a list of and extracted contract code. Proving effort is executing, and verification effort is linear. It depends on the number of transactions. The previous ones, the verification effort didn't depend on number of transactions. It was pretty constant based on just number of blocks. And what I'm trying to, in fact, say is that I think that for our use case, this BFT core in light client mode makes, in fact, sense. Because at least my gut feeling is that up to like 1,000 transactions per second, it is even easier to validate or verify from BFT core than ZK proofs. And we do not have to do any proving at the EVM side. So we have a finality in like a couple of seconds, no proving, but the security is even stronger than in case of ZK. Okay, but yeah, the proving, the ZK proving can be accelerated by running or using the GPUs. Here I have an example from a presentation from Etrex guys. So they show that they can validate the block using one high-end gaming GPU in like 2 to 12 minutes, depending on block size, and running like 16 highest-end consumer GPUs. The block validation or proof generation can be done in seconds. No, it's not SP1, it's some different experimental backend, but whatever. And we can use SP1's proven network, and then we have to pay for every individual block. And it has some funny security model, so I wouldn't consider it. And go on with implementation. So it's a different repository, which is using Etrex as a submodule or sub-repository, and it's a branch called L1 at the BFT core repository. So what happens is that block is produced by a custom crate on this repository, but it's executed by Etrex. Proof coordinator is custom, but the proof generation is based on Etrex. And the guest program which runs the verification to generate the execution trace is custom, and the BFT committer to submit to layer 1 is also custom. But the main functionality comes from executing a block and proof generation from the Etrex side. And then block certification request goes to BFT core. The input record is not modified, but the certification request has one extra field, which is a ZK proof blob. And the BFT core itself is written in Go, and that's why it was necessary to extend it with some Rust library, which is called through a C language wrapper. But it seems that it works pretty well. There are like many layers. So Go is like easily extendable with C language, and Rust library can export functions using like C calling convention. Yeah, so this is how this block certification request looks like. There is only one extra field. This is an extra function which is used in a BFT core main execution loop or validation loop. It takes this block certification request and has access to input record. And also it uses shard information to validate if this proof is related to a specific shard. And configuration has like 3 different flags: CK on/off, prover backend, and what's the verification key. Verification key is basically the thing which authenticates the prover's statement. Now we can think about it as a hash of a guest program, which validated the public input, private input pair when we did run it in VM. And this is what connects the prover and the validation side. So we have to manually extract this proof and copy it to the validator at BFT core side. And yeah, it was not trivial to put together the actual SP1 library-based validation, which can be used for from a Go program. There are a couple of layers in between. And that's all.